Hello, I'm Rajdeep, and I'm a PhD student at UC San Diego, and I will be presenting my work at SIGCOMM', which is about memory management in ActiveRMT. So as many of you are aware, there's an ecosystem of programmable switches based on RMT, commercially available as Tofino, and these switches allow application-specific functions from a variety of sources to be deployed on the network. However, RMT switches are shared resources and can only run one program at a time per pipeline. So individual programs have to be compiled into one monolithic program by someone, for example, the network operator, before deploying them on the switch. Now, this can become a tedious, if not intractable task, and we do not know of any approach that is able to automate such a task for arbitrary programs. Needless to mention, the current ecosystem is also limited in its ability to perform runtime updates. So the process of updating RMT pipelines is not hitless and causes a network disruption when resetting the switches. So we came up with an approach called ActiveRMT that enables one to allocate and run programs from individual sources on RMT switches. Using capsule-based active networking, each packet contains a distinct program which runs on these switches. A controller monitors and manages switch resources to smartly accommodate more applications on these switches. And as for security, we assume a network where packets can be authenticated at source, for example, using access control lists. So a user deployment model looks something like this. Individual users can write applications that insert active programs into network packets. The packets can then be used to invoke user-defined behavior on the switch. The deployment process itself consists of three phases. In the first phase, the client requests an allocation for the program it wants to deploy over the network. The controller accordingly responds with an allocation. The client then uses this allocation to synthesize an active program and then encodes this program into network packets before putting them on the wire. The activated switch runs a P4 program, which decodes and executes packet instructions. We call it the switch runtime. We statically allocate a set of match action stages to run active programs, where each active stage runs one instruction. RMT stages are all identical, so that allows any instruction to run on any stage. Packets can be recirculated on current devices, so programs that are longer than the number of stages can recirculate and run to completion. This, of course, costs additional bandwidth and is something that the programmer has to keep in mind. Stateful applications require reserving switch memory, and multiple applications cannot be accommodated without sharing memory. And so in the remainder of this talk, I'll talk about how to perform memory management on ActiveRMT. When allocating memory, we use a memory layout which consists of a two-dimensional array of memory blocks. Each block has multiple 32-bit memory objects, and the granularity of this can be configured at runtime. We use physical addressing since virtual addressing is expensive on current devices. What we do instead is we perform memory protection using DCAMs, an approach which also allows fine-grained memory partitioning. To make a better memory allocation decision, we identify applications as one of two types based on their memory utility characteristics. We refer to applications as inelastic if they have a fixed demand, and elastic if they have a variable demand, and their utility increases with more memory. Before describing the memory allocation process in more detail, let's first consider an example program, such as an in-network cache. So that's a program that can read a cache object from switch memory. This program that you see over here has three memory accesses, one corresponding to each memory read instruction. And so it requires three memory stages. This application also has elastic properties, which means that its utility increases with more memory. When the controller attempts to allocate this application, it allocates the entire set of memory blocks corresponding to those three stages. When another instance of the same program arrives, the controller can simply split the same set of stages between the two applications. However, the first application now has to yield some of its memory, and this causes a temporary disruption to its functionality. We refer to this as a reallocation cost, but there is a way to avoid this cost. Since memory is fungible and the runtime is functionally redundant, we can run any instruction on any stage. So we can simply push the instructions down to avoid memory conflicts. We call this mutating the program and the corresponding program as a mutant. The controller takes advantage of mutation when making an allocation decision. Mutant programs are synthesized by the client upon receiving an allocation. Here, the mutants have allowed the controller to allocate a mutually exclusive set of stages to each cache instance. So not only does mutants allow us to completely deconflict, as we see over here, it also helps improve utilization by giving more memory to the applications. To see how this benefits applications, let's consider a scenario where we introduce a set of 4 cache applications that arrive 5 seconds apart. So the first application arrives at time t equals to 0. For sake of simplicity, we populate each cache instance upon allocation. We also choose a workload with which we are able to achieve a maximum possible hit rate of around 85%. The time taken to activate an application is the time taken by the client to coordinate with the switch, which is request an allocation and receive a response and so on, and also the time taken by the controller to compute the allocation and provision the switch accordingly. The second application in the scenario arrives at time t equals to 5 seconds. The controller is able to find a set of stages that does not conflict with the previous application, and hence the first application remains completely unaffected by this allocation. A third application arrives at time t equals to 10 seconds, and the controller is once again able to find a set of stages for this application that does not conflict with any of the previous applications. However, when the fourth application arrives at time t equals to 15 seconds, the controller is not able to find a mutually exclusive set of stages for this application, and hence it chooses the first application to share its memory region with the fourth application. This, of course, causes the first application to suffer a brief disruption because it has to yield some of its memory. This disruption is around 100 milliseconds in this case. Note that the second and third applications still remain unaffected upon arrival of the fourth application. The total allocation time for the fourth application is just a few hundred milliseconds. In practice, we can have a lot more applications. So if we simulate an increasing population of 3 types of applications over time that follow a Poisson distribution, so where in expectation, 2 applications arrive and 1 departs every time tick. We look at 2 types of allocation modes, one of least constrained and the other of most constrained. In the least constrained allocation mode, the controller chooses a scheme that allows recirculations to find a better allocation, whereas in the most constrained mode, it does not consider such recirculations. We see over here that in the least constrained mode, the system is able to achieve almost 100% utilization initially. But in any case, both these approaches eventually stabilize to around 75%. So in conclusion, we present a system that allows rapid, non-disruptive provisioning of user-defined applications on programmable switches using capsule-based active networking. Our approach does not require operator intervention to reprovision the switch for a combination of services. Our mutant-based allocation approach allows us to accommodate more applications while simultaneously achieving better memory utilization. Our approach also enables non-disruptive provisioning of application functionality on programmable switches. One of the drawbacks of our approach is that certain types of functionality, such as firewalls, cannot be implemented because of the trust model. And this is something that we plan to address as a part of our ongoing work. And that would be the end of my talk. Thank you.